Hello, this is an explanation on the Pixie Evolution Simulator. This is my third version of an evolution simulator, improved with the experience gained from the other ones. I will first talk about the evolution simulator, then talk about the differences to the other ones, and give an outlook of what I'm planning for the future. Each of the colored squares represents an individual creature. I call them pixies, as they are just a bunch of colored pixels. The green squares are plants. They serve as food source for the pixies. If a pixie gets killed, it leaves red squares. These represent meat that can be eaten as well. Now, what makes this an evolution simulator? Each of the creatures have an individual neural network. The prerequisites needed for evolution are reproduction, mutation, and competition. By spending a high amount of food, these pixies can split themselves to reproduce. Each time there's a chance of a random mutation. Each mutation changes the color, so similar looking creatures are closely related. The mutations can change the size, the amount of spikes they have, the structure of the brain, as well as what kind of senses they own. Competition is quite self-explanatory. The amount of food is limited and they can kill each other. This in theory should lead to an evolving set of creatures, similar to animals in the real world. To understand the simulation, I will now go into more detail. Each time there are no creatures left, I will spawn in a set amount of them. If they manage to survive, the simulation continues and they reproduce and evolve. To keep the environmental pressure high, I decrease the amount of food gained by each plant proportionally to the amount of creatures that are currently alive, meaning that the better a species gets in surviving and reproducing, the deadlier the environment will become. Plants spawn at a constant rate till they reach a specified threshold. The senses of a creature can include a touch sense, so they get an input if they are next to a plant, meat, or a creature. Additionally, they sense how different the creature's color is to discern if they are mates or enemies. They can see in straight lines and can evolve clocks that give a signal each n ticks to have a feeling of time. Each of the creature starts with the input senses of how healthy they are, how much food they have, and how far they are away from the border of the map. The output of the neural network decides multiple choices. First of all, the movement. They can choose between standing still, moving in a direction, or moving in circles of different radii. The second decision is what bonus action they want to take. They can choose between different options like reproducing, healing themselves, or doing nothing. Third one is the interaction they choose if they move into another creature. They can choose to hurt the creature or to just ignore it and stand still. Or they could even choose to feed it and exchange information with the creature. The amount of food that they consume is proportional to their size, the amount of spikes they have, and the size of their brain. Different actions need different amounts of food. Standing still takes less energy than moving. Now to the difference to my other evolution simulator. My old simulations were written in C# and used the Unity engine. This time I decided against the Unity engine as there's just too much overhead that I don't need for the simulation. Instead, I wrote it in Java using Swing for visualization. I directly used a hash map this time that uses the RGB value as a key to link to the Pixie class. This made it easy to use the buffered image as a representation of the simulation. In my old simulation, I programmed the neural network framework myself. As I'm quite sure that other people can write way better optimized code, I decided to use a machine learning library this time. I chose the popular NCOG library, for it is quite easy to implement. This meant that I couldn't use the near evolution of augmented topology, or NEAT, as it didn't support the NEAT topology in a way that worked with my simulation. I instead opted for a classic feed-forward neural network with fixed layer size to increase the performance gained through being calculated by matrix multiplication. This directly leads to my future plans with the simulation. I still think that the NEAT system leads to better and faster evolutionary behavior. Writing a fast NEAT framework will be my next goal, as I wasn't happy with the performance of my last NEAT framework that I wrote. If you want to improve or play around with my simulation, you will find the repository on my GitHub Cream Soda Codes. I'm always looking forward to improvements, as it will increase the chances of interesting behaviors to evolve in a reasonable time. Thank you.